Good day everyone, I am here to present about the application of terrestrial LiDAR for geohazard mapping, monitoring, and modeling in the British Geological Survey by Lee Jones and Peter Hobbs. A journal review by me, Carl Dennis P. De La Vega, and I am from BS Geodetic 3101. Let's get a move on what I know about terrestrial LiDAR. I have knowledge of the application of terrestrial LiDAR or light detection and ranging technology for geohazard mapping, monitoring, and modeling as implemented by the British Geological Survey or BGS. Terrestrial LiDAR is a ground-based remote sensing method that provides highly accurate and detailed three-dimensional data of Earth's surface. The BGS leverages this technology to analyze and document geohazards such as landslides, rockfalls, sinkholes, and coastal erosion with exceptional precision. This technology enables the creation of high-resolution digital terrain models or DTMs and digital surface models or DSM, which are critical for visualizing geological features and detecting subtle changes in the landscape. By conducted repeating scans over time, BGS can identify and monitor dynamic processes such as slope instability or material displacement, providing valuable insights into a geohazard behavior. Furthermore, the integration of terrestrial LiDAR with other geospatial datasets such as satellite imagery, aerial LiDAR, and ground truth surveys enhances the understanding of complex geological systems. This comprehensive approach allows for the development of predictive models, enabling the BGS to assess potential risk, improve hazard mitigation strategies, and improve land use planning and policy decisions. Through these efforts, the BGS plays a crucial role in protecting communities and infrastructures from the impacts of geohazards. So the next slide will mainly focus about geomatics. The British Geological Survey (BGS) geomatics capabilities have been utilized in a variety of scientific studies such as the monitoring of actively growing volcanic lava domes and rapidly retreating glaciers, coastal erosion and platform evolution, inland and coastal landslide modeling, mapping of geological structures and fault boundaries, rock stability and subsidence feature analysis. And lastly, geoconservation. The following will further be discussed in this review: terrestrial LiDAR, mapping, modeling, geohazards, and monitoring. So the challenges and risks of geomatics. Quality of data. LiDAR data can be affected by a variety of factors including the type of surface being scanned, weather conditions, and the calibration of the sensors. The application of LiDAR in engineering geology. The first example is mapping. LiDAR data can be used to map bedrock formations, superficial deposits, and geologic features like faults and sinkholes. The next one is hazard assessment. LiDAR can be used to assess the risk of geologic hazard like landslides, tsunamis, floods, and lava flows. Third one is fault detection. Fault detection methods such as built-in tests typically lag the time that the error occurred and either trigger alarms for manual interventions or initiate automatic recovery. This is mainly used when seismic shock or earthquakes will occur. Next one is mineral resource identification. Mineral resources are identified by examining their physical properties. That includes their substance with distinctive chemical and physical properties, composition, and atomic structure. Mainly, minerals are identified with their physical properties such as luster, streak, and crystallization. Yes, and limitations. Despite its advantages, the application of terrestrial LiDAR faces some limitations. Number one is weather dependency. LiDAR surveys are sensitive to weather conditions, with rain or fog potentially degrading data quality. It basically means that these factors can alter the quality of data or the image provided by LiDAR. The second one is data management. The vast amounts of data generated require robust storage, processing, and analysis capabilities. In doing LiDAR surveys, having a big or mass storage needs to be considered in order to efficiently create a reliable LiDAR survey. And lastly, field accessibility. Deploying LiDAR systems in remote or hazardous areas can be logistically challenging because it involves some risks like having some parts of the area not visible or cannot be easily accessed by LiDAR because of the barriers inside the project area. Advantages and limitations. Despite its advantages, the application of terrestrial LiDAR faces some limitations. Number 1 is weather dependency. LiDAR surveys are sensitive to weather conditions, with rain or fog potentially degrading data quality. It basically means that these factors can alter the quality of data or the image provided by LiDAR. The second one is data management. The vast amounts of data generated require robust storage, processing, and analysis capabilities. In doing LiDAR surveys, having a big or mass storage needs to be considered in order to efficiently create a reliable LiDAR survey. And lastly, field accessibility. Deploying LiDAR systems in remote or hazardous areas can be logistically challenging because it involves some risks like having some parts of the area not visible or cannot be easily accessed by LiDAR because of the barriers inside the project. Now let's move on to future directions. The review identifies several improvements for future research and development. Number 1. Automated data processing. Developing machine learning algorithms to automate the processing and interpretation of LiDAR data could significantly enhance its usability to help during LiDAR survey. Number 2. Integration with UAVs. Combining terrestrial LiDAR with unmanned aerial vehicles or UAVs could overcome field accessibility issues and expand coverage of the area being surveyed. Lastly, real-time monitoring. Advancements in LiDAR technology could enable real-time monitoring, providing immediate insights during geohazard events, and it could potentially give crucial information on what is happening in the surveyed area. Now let's get to the point where I will share what I have learned about this journal review. So, the British Geological Survey use of terrestrial LiDAR highlights how important it may be for managing geohazards. LiDAR technology facilitates informed decision-making and proactive hazard mitigation by delivering high-resolution, precise, and timely data. LiDAR will probably become even more useful in addressing geohazard as it develops further and is integrated with other technologies. So the application of terrestrial LiDAR by the British Geological Survey represents a significant advancement in geohazard science and risk management. This ground-based remote sensing technology provides unparalleled accuracy in capturing detailed three-dimensional data of Earth's surface, enabling the creation of high-resolution digital terrain and surface models. These models are instrumental in visualizing geological features, identifying subtle landscape changes, and monitoring dynamic geohazard processes such as landslide, rockfalls, sinkholes, and coastal erosion over time. By integrating terrestrial LiDAR with complementary geospatial datasets, including satellite imagery, aerial LiDAR, and on-ground surveys, the British Geological Survey gains a comprehensive understanding of complex geological systems. This multi-dimensional approach supports the development of predictive models that anticipate potential hazards, informing effective mitigation strategies and contributing to resilient land use planning and its infrastructure development. Through this effort, the British Geological Survey not only advances the science of geohazard management, but also plays a critical role in safeguarding communities, infrastructure, and the environment. The application of terrestrial LiDAR underscores the importance of leveraging cutting-edge technologies to address geological challenges in a changing world. So that sums it up on what I have learned about this journal review. That is all. Thank you.